Good morning, everyone. I welcome you all for today's webinar. Last webinar we have already seen on inverse and composite functions, and I hope everyone of you all have enjoyed the webinar. So, moving forward to our next series of webinar, today we are going to focus on logarithm and exponential functions, which will be taken by Mr. John Paul. So, over to you, sir. You can start sharing the screen.
All right, thank you so much. First, can everyone hear me? Can everyone just give me a thumbs up or something on your that you're able to hear me? Is my audio clear? So
Yes, sir, you are audible.
can you hear me? Can you guys hear me?
Yes, we can.
All right, cool. Thank you so much. All right. Good morning, everyone. Students, teachers, everyone from TIA. I can even see Jimmy here. Good morning, everyone who's joined in. I'm quite excited about today's webinar, and one of my favorite topics, in fact. At the same time, I must be very honest. Okay, it just, when I wrote the agenda, when I planned the agenda, I thought that this is quite deep, and I'm not really sure how to go about it, in the sense, every time I ask students, where they are at in their schools, with what we're covering. And like, I think even last time when we met the Saturday before last, several of you who were there said that they had not done composite functions or inverses. So kind of, I said, okay, let me go through the theory a bit, which is what sometimes I get a little nervous. I want to know where you are all at. And there's a very specific reason we chose to do exponential and logarithmic functions after we've done inverses. There's some kind of a logical progression to, the idea of inverse functions and why exponential and logarithmic functions. So first, like I said, this is one of my favorite functions. Even when I teach IB and, A-levels or whatever I teach, I talk about exponential functions being one of my favorite functions when it comes to differentiation or integration, but, we'll keep that favoritism for some other day. But even though it seems like just I've jotted down 3 points, it's actually a lot. All right, for those of you teachers, educators out here today, you might know that this is a lot to be covered in just a span of 1 hour. And I don't like it just talk. I like students to also interact, which makes it even longer, So just to give you a heads up, what I mean by that is, to back it up, I have got questions from the IGCC. Always I try and tackle that. So I do a little bit of theory, and then I'll go ahead with the problems. The first set of problems might seem or will seem similar to some of the other things when we were doing solving equations. If you look at it, it's just that now we have a log term there, so it becomes a logarithmic equation. You have an exponential term there, so it becomes an exponential equation. And then you have something to do with graphs, and we've seen so much about graphing with functions, and there you can see a little term there with an exponent and a little polynomial fused together. But the same kind of ideas, minimum points, and what's the coordinate of that local maximum point, and to solve an equation, something like that. And the second set is slightly different, which has got the logarithmic graph there to a base, and then using the graph to solve equations as it's given here. But the most important, and I doubt we'll even come here, but I can just request maybe Swati and everyone who's on the numerical analytics team that maybe if you're not able to do this, the most important place where you will see exponential and logarithmic functions either coming together or on its own in the IGCSE examinations is in paper 6. For those of you who are in grade 9, I can see one of my students, I don't know why, he always comes here, even though he's not grade 9, but that's okay, everyone is welcome. Is paper 6. And for those of you who start in ninth grade, probably in your schools, you've not even, has anyone heard of paper 6, just out of curiosity? Paper 6 in your schools. Has any student, if you, those are 9th graders, okay? The 9th graders, any student here, if you've just raise your hand saying that, yes, I have heard about paper 6, or anyone? Any student just wants to respond to that? Paper 6. There you go. Somebody, Adit has said so. All right. Anyone else has heard of paper 6 in your schools? Did any of your school teachers, did they brief you about paper 6? I think one of the highlights of this particular course, International Math, compared to any, whether it's a 0580 or even if it's 0606, I think 0607, which is our current course, which you're talking about, this paper 6, one of the highlight is the paper 6, all right, which deals with modeling and investigation. And the question that I even chose, if you get time, we'll definitely go through this, but we may even skim through it, is on modeling. As you can see, it starts very simple, but then it moves on to, it looks like a very simple function here for us, and then it moves on to something to do with exponents there. Okay, you can see something there, and there you go. There's another exponential modeling there. So in my opinion, I think even if your paper 2 and paper 4 do not contain many questions, it will definitely show itself up in a paper 6. All right, so be cautioned of that. I have one more example, but like I said, the reason I said that, I'm a little nervous about this, because I like to complete something. But even if I make you aware, that there's something called a paper 6, there, how it will appear, how this topic will appear. Because like I said, this is where you'll actually see the greatest application in the international math curriculum. So I always like to build the overview, the broad picture before I jump in. Where, to what extent is this topic going to come in? Also, you will, in your syllabus, it might just seem like, very, very few bits that's covered. But, as you proceed, as you progress into grade 11, grade 12, whether it's A-levels or whether it's IB, you'll go into a lot more details, and you'll see the real power of exponential functions and logarithmic functions and the interrelationship between them. So this is definitely where I would say in paper 6 is where you'd see a lot more of its application. As opposed to what you see here in paper 4 kind of questions, and paper 2 might be even simpler than that. So with that being said, like I said, even though it looks like just 3 things that I've put together, it is a lot. So I just say I wish myself some luck, good luck to try and covering as much ground as possible. But let me start with the story. Okay, I'm going to start with the story. Many of you must have heard the story in different forms, in different ways, but it's okay. Let's hear the story again one more time. Ready? Everyone ready? All right, here we go. Let's roll the video and we will listen to the story.
Legend has it, at the time, the king of Ambalapooza challenged a travelling sage to a game of chess. If the sage was to win the game, he could ask for any reward he wanted. Sure enough, the sage won the game, and when the king offered him his reward, the sage asked for the following: give me 1 grain of rice on the first square of this chessboard, then 2 grains on the next square, 4 grains on the next, 8 on the next, and so on, so that each square has double the amount of the previous. Well, the king was very confused with this. Didn't the sage want some treasure? Anything else he could offer? No, the old sage stuck with the rice. So the king got his officials to collect together the rice, and he started putting it onto the chessboard. He put 1 grain on the first square, then 2 grains on the second, 4 grains on the third, then 8, 16, 32, 64, finally 128 on the last square of the top row. It was looking good for the king so far. This wasn't a big reward. So he started onto the second row. 256 grains on the first square, then 512, and the numbers just kept getting bigger and bigger and bigger, until by the end of the second row, the king needed 32,768 grains. He was starting to get a bit worried by now, but he kept on going. By the end of the third row, he needed 8.4 million grains of rice on that last square alone. He kept on counting. By the end of the fourth row, he would need 2.1 billion grains of rice. Now, he didn't have this much rice, but he got his officials to do their working out, and they calculated by the time he reached the end of the chessboard, he would need 9 times 10 to the 18 grains of rice on that last square alone. That's 9 with 18 zeros after it. And by the time the chessboard was full, the king would have needed to give the sage 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615 grains of rice. That would weigh approximately 210 billion tons and would be enough to cover the entire country of India with a metre-high layer of rice.
I'll just stop that video there. I like that story, even whether it's true or not true, that doesn't matter. It just shows something very, very shocking. I like that word, how I use that word to describe shocking, because initially it doesn't seem like a lot, the way an exponential function behaves. And many of you must have heard, like I said, the story in different ways. Initially, it doesn't even seem like it. Today we are having this webinar online. Many of you are having classes online. Many offices, many factories, many events are taking place online. Many math competitions and quiz competitions, and even your MUN is happening online, because we are also stranded in our own homes because of a pandemic. And initially, when you saw the news of how things were increasing, it didn't seem like a thing to worry about, because initially, the numbers were quite low, and it seemed quite low. But then all of a sudden, the trajectory started shooting up like anything. All of a sudden, and the question was always, when would that happen? It's quite deceptive when it's at that stage. You never know what's going on here. This kind of rise is what's called an exponential rise or increase. You really don't know what's going on. And this is just through images, through graphs. The chessboard thing was fantastic, because the first row, the king must have thought that's not much, first grain of rice. It's like looking at this part of the graph. The first row, the second row is not much. Now, all of a sudden, when you are crossing the fourth row, and that's when the king starts worrying. And it doesn't take much time. It's not like you have to reach, 100 rows within the 8th row. You saw that sentence, I don't know how they calculated that there was enough to cover the whole of India, 1 meter depth or something like that. I don't remember, but if you're interested, I can show that video, or pass that link to that video some other day. Just a sec. Sorry, there was a phone call. I just had to cut it off. So yeah, that's the shocking part of an exponential function, where initially it doesn't even look like it's increasing, but all of a sudden, within no time, suddenly, and this is like literally like saying within no time, that doesn't take much time, within no time, it just shoots up like any crazy function. It just goes up. And the reason is because in every other equation, that variable, that wonderful variable we refer to as x, is the base. You know what I mean by base is something like this. You have x squared for a quadratic. So that's your base. And the square, the 2, is the index. That's your index. In some dictionaries, you hear the word exponent for that. The number is the exponent. The number is the exponent, whereas the variable is the base. Okay? So even if it's a cubic, or even, a cubic function, there you go. The number is the exponent. The variable is the base. Now, the difference now in this exponential function is that it's getting reversed. The number is the base. The exponent, that thing, is the variable. You have a variable exponent. All of a sudden, the nature of that function, the behavior of the function, is a lot different from any of the standard polynomial functions that you may have come across. Okay, so that's the beauty and that's the shocking part of it. However, another part of the history or the background of exponential logarithmic function is this. Exponential functions are the most naturally occurring functions. Okay, let me put that thing here. Exponential functions probably are the most natural. What I mean by that is that, whether you're looking at, I gave the example of the growth of a virus, whether you're looking at the growth of any bacteria, whether you're looking at even radioactive decay. I mean, that's a decay. You learn about exponential decay later on. Anything that happens in nature can be modeled, the growth of anything, even money for that matter. You may have studied compound interest, earlier on, and in fact, one of the first sessions we might have talked about compound interest. Compound interest is an example of an exponential growth, by the way. People prefer compound interest because, it grows. And the way it grows is an exponential behavior. All right. My point is, exponential function is the most naturally occurring function compared to logarithmic functions. Now, let me tell you a little bit about this logarithmic function. Logarithmic function is man-made. It's almost like you can use the word invention. It was a human invention. Exponential function, naturally occurring function. And you know what's the funny part? In mathematical history, the first of these two, let me just give it away first, okay? These both are actually inverse functions. They both are inverses of each other. And last Saturday before last, we spoke about inverse functions. They both related to each other in the fact that they both are inverses of each other, okay? But the first function of these two, even though exponential is a naturally occurring function, that means it was always around us. The first one that came across to human beings was the logarithmic function. There's a man by the name John Napier, and the reason even he came up with a system to multiply and divide larger numbers. What do you mean by larger numbers is, 6 digits and 7 digits and with decimals. Because of business, economics had come to a standstill. This was the days when there was no calculator. He came up with a system to multiply and divide. Very long story, maybe even boring story, and maybe it will go beyond your head. But the point that I really want to stress is it was a man-made attempt, human attempt. They did not even know anything about exponential functions back then. And it was more than 100 years. I would love to say 300, but at least definitely I can say it's more than 100 years later, they came to realize about another function, the function called exponential function. And they found out that, hey, they are actually inverses of each other. So it's quite an interesting story, the development of both exponential and logarithmic functions. One is a naturally occurring function. The other one is a man-made function. And the funny thing is that human beings got to know about the man-made function first because of John Napier. He came up with a system, just a system. It's a very, very arduous system. And today you might not even want to use it because we have calculators around. But that's the story, how they're linked. A man-made function is the exact inverse of a naturally occurring function. How absurd, how strange is that? I find it quite strange. And I always like to talk a little bit about that when we're talking about the history or the background of exponential and logarithmic functions. And like I said, they are inverses of each other. So let's just quickly look at, this logarithmic, the idea of the relationship between the two. Okay. So here's how they're related. If you had three numbers, A, B, and C are three numbers. Okay. Such that A, let's change the order. I like to put it as B. B to the power of A is equal to C. Okay? I deliberately put B because, B for base. Base, as we saw, base and index, and that's your exponent. Okay? A is the exponent, B is the base, B for base. That's the exponential form, all right? If you have three numbers like that, the log form is actually A is equal to log C to the base B. Okay, that part you need to be careful. That's why I put B for base so that, whether you write it in this is called the log form. Whether you write it in the log form or whether you write it in the exponential form, The base I have denoted by the same letter, b for base. B to the power of a is equal to a c. B to the power of a is equal to c. Then a is log of c to the base b. There are some properties of logarithms also that come into play. All right. For instance, the log of 1 would be 0. All right. The log of a product would be equal to the log of the sum. Any base. The log of a quotient would be equal to the difference of the logs. And there are some special properties also, like the log of a power. Let's put it as some p for power, is equal to p times log m, that base. Okay? Those of you who have not done this in school, don't worry about it too much if these laws and these properties seem too overwhelming right now. Eventually, you will get to see it in your school also. It's just giving you a little overview, perhaps, if you've not done. And if you've done, then it's a good, thing to just, recap or, just keep it in mind. All right? And these properties are what we need to use in some of the questions where you have to, either condense it or, write it in some forms. I'm just seeing whether we need to have any. This is one. And this, okay, yeah. Logs, typically this base b, if base b is 10, like we have the base 10 decimal system, right? If the base is the decimal system base, we call it the common logarithm. Common logarithm. Okay, so a log of some x to the base 10, that's a common logarithm. And whenever we talk or we refer to common logarithm, we can even ignore writing the base. We don't have to write the base, okay? Because, it's a common logarithm. You don't even need to specify what the base is. However, when the base b is a number e, e is an irrational number, e is an irrational number. For the time being, let's just keep this thing in mind, all right? E is an irrational number between 2 and 3. E is an irrational number between 2 and 3. When the base is e, so it becomes like this, we call it a natural logarithm. Like I said, the naturally occurring function, and it's often represented as ln of x. ln, all right? ln of x means the base is e. ln of x means the base is e. So, without any further delay, let's just look at how it plays out, okay? And if there's something that I've left out, I'll come back to that a little later on. Let's just look at some problems, okay? So here we go. This is one problem, set 1. It says find x in terms of p and q. You just have to use some algebra skills and some of the properties of logarithm to write x in terms of p and q. So you've got that nice equation, 3 log p plus 2 log q minus log of 6 is equal to log of x. And the idea is to reduce the left-hand side using the properties of logarithm, meaning to one term, writing it as one term using the properties of logarithm. And, comparing with the right-hand side, you can tell what that x is. That's the idea of how we'll go about this question, all right? So you've got these two terms, right? You got 3 log p and 2 log q. 3 log p and 2 log q. Let's combine them using the power rule. If you recall the power rule, if I go back to the power rule one more time quickly, that power rule for logs, look at that. Log of m to the power p is p log m, all right? Someone asked a question or something? I need, okay, no, what's that?
It is E is Euler's constant, right?
E is not, actually it's not, yes, Euler has something to do with it. You're right on that, you're right. But it is. I must be fair and say that it is, okay? And he had a lot to do with even bringing that letter E into, because it was there even initially because, like for instance, the letter pi, it's a Greek letter, right? And it's denoting the ratio of the circumference to the diameter, right? We denote it with the letter pi. It seems like the Greeks came up with the idea, but not true, right? I mean, that idea was there before. So similarly, E, even though the credit is given to Euler's, he was not the first person to come up with the idea of E, is what I'm trying to say. Just as the circles, if you understand the idea. The idea of E was already there in many places. People are using it without maybe referring to as E. So I'm a bit picky about who gets the credit. Like for instance, I spoke about pi. Greeks should not be taking the credit for something that was being used, whether it was in India, whether it was in Egypt, or even in China for that matter. The idea of the ratio of the circumference to the diameter, it was there already. So in one sense, yes, you're right when you call it the Euler's constant. I know we are referring to the same thing, if that's your question, but. Yeah, I mean, I'm a bit picky about who gets the credit for the right thing, So it's been used in several civilizations even before that. So yeah, not as the letter E as we know it when Euler formalized it. He formalized several things. Even he formalized I. That the complex number. Anyone heard about that imaginary number I, the square root of -1? I think he formalized and. So Leonardo Euler is quite popular for that. So yeah, let's not stray from that. But I'm glad you guys are listening. I'm glad you guys are also reading.
Sorry to interrupt, sir. Yes, Adit, you can speak. I've unmuted you.
Oh, he had a question?
Yeah, he just raised his hand.
Oh, I'm sorry. Yes, Adit.
No, I raised my hand just to say that I know the letter I.
Okay. All right. Okay. All right. Okay. Fine. Good. I'm glad to hear all this. I'm glad that you guys are reading a lot more than what's there in the syllabus. That's fantastic. That's fantastic. All right. Let's use the properties of logarithms and now try and reduce this left-hand side. Okay. So you've got log p cubed and log q square minus log of 6. I'm just writing the left-hand side, okay? And again, that's the power rule. That's the power rule used only the first two terms. Now, if you combine these two using another rule, which is the product rule, you can say that is log of p cubed times q square minus log of 6. Now, if you use still the other rule, which combines these two using the quotient rule, you can say that is log pq q square over 6. That's your left-hand side. On your right-hand side, of course, you just have log of x. Now, when you compare left-hand side and right-hand side, you can say that, that x must be equal to p cubed q square over 6. Okay? So that is just using the algebra of logs, the properties of logs, and then comparing two sides and figuring out. There's one kind of question that you will see in your paper 4. Another kind of question is when you have to solve the equation. All right, solve the equation, this exponential equation given to you. And if you recall the property that we said, if there are 3 numbers, b to the power of a is equal to c, then you can write a as log c to the base b. All right, that's converting from exponential form to log form. All right, so you could use that in this in this part B and say x must be equal to log of 6 to the base 4. Log of 6 to the base 4, and then you have to use your calculator, and that's what we are all about here. So another question, somebody wrote something on the chat. All right, okay. All right, let me share the calculator and just show you where exactly to find on your calculator. Okay. All right, why am I not able to find my calculator here? Here we go. This is the non-CAS. This is the non-CAS Inspire. So those of you who've been with us throughout several Saturdays, you already know that this is a very important key to find out all your templates. All right. So you can go there directly, or you can find log key here. All right. There's e to the x here. This is on the same row as 1, 2, 3. Okay. if you can follow along my arrow where I'm pointing to. So there's an e to the x here. So when you hit e to the x, you'll get e to the blank, and you can put some number there if you're evaluating something. Okay, that'll give you 7.39. If you're doing some calculation with that, let's say you had a a ratio of something. So just making up some ideas here. So here you probably have, say, e to the power of 5, something like that, and there you go. All right, so you can calculate using that, and you can combine with 10 to the power of x, or if you hit control, that 10 to the power of x, you'll get that log, that template I was talking about, that log of something to the base something. Okay, that's one way to look for this template. The other way, which I normally prefer and ask my students to go straight into this key here, and you can find you can find log. Okay, yeah, here you can find e, and you can find log here. Can you see that? You get all the templates here. So this is a very handy tool to keep in mind, even if you're not able to read through this templates key here on the right hand side of 9. If you go there and if you just hit this key, and there if you put down, you'll get that same thing. And here we put down our value, log of 6 to the base 4. Log of 6 to the base 4. All right, and it'll calculate what the value you need. Okay, 1.29 it says. So that's, I think, 3SF it's set to. Let me just check what the settings are here on my calculator. Oops, sorry. On the settings, I go to my document settings, and yes, it's 3SF. So that's the numerical value of 1.29. There is also one more rule, the change of base. I did not talk about it. I'll just look for it if it comes through. I didn't want to just bore you guys with too many rules. I just thought, perhaps, the better thing is just for you to see how these questions come in the papers. The part 2 is a multiplication of brackets, and that's not necessarily exponent or log, so I'll ignore that. Okay, I mean, that's very simple or straightforward. You should be able to do that. So let's look at number 4. Okay, something to do with the graph. Now, again, this is a graph question. We've seen graph before, which is why I said, some of these templates, some of these keys you must have seen in the earlier workshops, but now you're seeing it at this term, exponential term. So let me go through this also for you. The function is defined as 2 to the x minus 1 by 3x cube, and the question requires you to graph it between -2 and 8 on the x-axis. For x value is -2 to 8, and the y values are -12 to 10. So I'm just going to use the same calculator and go to do that. Local minimum, local, they said y coordinates of the local minimum points, coordinates of the maximum points, and then to solve that equation. So we'll come to that solving the equation part sooner. Okay, so I'll do this thing for you guys. And for those of you who've been through us, throughout this webinar series, you must have seen this thing before also. Okay, so I'm going to do this graph quickly. I'll go to the calculator, and my favorite tool, I think, not just favorite, I think the most powerful tool I would say for grade 9 to use is this assigning key or the define key. So, because, we've seen before how we can link pages, how we can share the pages. So I like to do this. I mean, you don't have to do this linking, because in this particular question, as you saw, you're just using it in one context. You could have gone straight to the graph page. I'll do it anyway, all right, this way. So you could have still, like I said, you could have gone straight to the graph page, but, never mind. I'll define it here. 2 to the power of, that's the key, all right, the hat key here. That would give you the power, 2 to the power of x minus, you have a fraction, always use this fraction thing. It's 1 over 3 x cubed. All right, be careful how we use this. Okay, 1 is again, that's the power, it's cubed. There you go. That's pretty much done. And the reason I like this key to define is that, this question does not ask, but even if you were supposed to find the value, at some value 2.1 or, some strange value 2.01, you can just assign it, and then you can say hit enter, and it'll give you the value, which is why I really like defining it before, and in this case, of course, they asked us to graph it. So let's just go and graph, okay? Add a graph page, and we don't need to type that because we've already assigned it. There's the graph. But you need to make some changes here to the viewing window as per the question, So they said it's -2 to 8. I'll make the change directly. For those of you who've been with us, you can either go directly here, -2 to 8, I think it said there, along the x-axis, and that's negative 2 to 8. Along the y-axis, the y values are negative 12 to 10. Negative 12 to 10. And if you don't know how to hit that or find difficulty, the way to do it is going to menu, and you have your window zoom settings. The first option is window settings. You can go there, and there also you can make the changes. Okay, here even if you want, you can make the changes to the scale, and you can say, you want it for every 1 unit, and you can hit tab, and you can go, and there you can say negative. Did it say negative 20? Oh, what did it say? 1 minute. Let me just check. It said negative 12 to 10. Sorry, negative 12 and to 10, and I can make that also 1. And this is one way to change the settings nice and clean. You'll get, okay. So if you're finding trouble to click that, you can go on menu and change the settings, and there you've got the graph. There you got the graph of the function, and basically you got to have just copied down onto your paper and find that. The second part of the question was to find the y coordinates of the minimum point. Y coordinates of the minimum point, you go to the menu, analyze graph, and it says minimum point, maximum point, whatever you need. You can find that, and you know that there's a minimum point here. All right, so you can click there, you can click there. That's the minimum point. Okay, there's also a local minimum here. But since they're talking about the minimum point of the graph in that domain from negative 2 to 8, that should be the answer. The y coordinate of the minimum point is negative 10.3. Negative. There's a question. Yes. How do we go to the graph? Oh, how do we go to the graph page? Thank you for asking that question. Let me back up a little bit. All right. So I was here. I was in the calculator page. What I did was I went to Control Doc. And that will give me the option to add a page. And I can add any page that I want. Okay, I can add a geometry page. I can add a list and spreadsheet page, a data statistics page, a notes page. In the earlier lessons, I think we have touched adding these pages. And even the notes page, I think we've spoken about. If you're interested, you can ask for one of the videos in the past. Didn't we do the notes page and all, Swati? I mean, just remind me quick. We've done
really,
that.
sir. Not really, but we have shown that maybe a little bit, 10 to 15 minutes.
Oh, that's good. That's enough. But I think I have spoken about the notes page.
Yeah, you only have spoken.
Yeah.
Right?
Was it for the IGCSE or the IB? But I did say that I'm not really. But it's a great page. Okay, the students were listening. I think I've shared that even in my class. I mean, it's a great. It should not be ignored. That's all I'm saying. So if you need to know more about the notes page or any of these pages, check out the earlier videos. And not just these webinars, okay, these Saturday webinars. I think Numerical Analytics, they've been doing a lot of webinars even before that. You can even look at how to add these different pages. And one of these pages is the graph page. Okay, that's what I did. So let me back up again. So we were in the calculator page. Control Doc will get you these options, and you can add the graph page from there. Or if you're worried, you go to the menu page. You just go to the menu page and you can choose one of those icons right sitting down there. You can just check that page and it can add you a graph page for you. Have I answered your question, brother? Adit? Yes? No? You have any other questions? Cool. All right, let's move on with this thing. So x coordinates of the max point would be the same way as I showed you the minimum point. Let me go back to that graph wherever I had graphed it. Where did I graph it? Oh yeah, there you go. X coordinates of the maximum point, somewhere there. They ask for so you go to menu, analyze graph, and they ask for the coordinates. So both the x and the y coordinates should be indicated in the answer. The last part in that question was about solving the equation. Let me flash that question to you one more time. All right. So here you go. This is the question that we are trying to attempt. It says solve the equation. This is the function. This is the function. And that is another one on the right hand. This is solve the equation for all real values of x. And they've given you 4 values of x. All right. So obviously they're looking for 4 different responses, and that's just 4 points. So don't worry about the algebra, because they've asked you to graph and they're expecting you to find the graphical solution. That's the expectation. Okay, so this is already our function. We've already defined this as a function. We just need to put this as a graph, and when they equal, which means it's talking about the point of intersection. So again, what we've done earlier on, how to find the intersection points. And obviously they are asking for 4. Some of you who have been earlier, you already know I like the point of intersection from the geometry option, because in one click you'll get all the 4 values. All right. So bear with me. I'm going to put in this as the second function, and we look for this for the point of intersection of the two. Okay. So back to our calculator page, our Inspire, the graph page. And I'm going to introduce a new function, and this time, just to introduce a new function, you hit tab. All right, tab is the shortcut key, and it'll give you the entry for a function. If you do not remember the shortcut key, you can always go to menu, and you can enter, okay, graph entry edit, and you can go to that. Once. All right. Okay. So let me just enter that new function that was on the right hand side. 2 times 1 minus x. 2 times 1 minus x is the function on the right hand side. So I'm just going to write 2 and 1 minus x. 1 minus x. And hit enter. There you go. That's a nice straight line. And they want 4 values. So there you go. That's the first value, the second value, the third value, and the fourth value somewhere, beyond our site right now. But we'll find that. Okay, we'll find that. If you want to see that also, you can go on menu, and you can go to Windows Zoom, and let's say if you say Zoom Fit, it doesn't fit well. Let me back up. So menu, Windows Zoom, data won't help. If I say Zoom Standard, would it help? Doesn't help. How do I get this? I want to see the 4th point. Zoom Decimal. Why do I feel that should help? There you go. It's not quite nice, meaning, but at least you can see the 4 point. There are 4 points. That's all I want to say, because the question shows you 4 points. You should know that there are 4 points of the 1, 2, 3, and 4, right? So for those of you who didn't know what I did, there are different zoom options here. When you go on menu, Windows Zoom, and if you're using, like say for data statistics, Zoom Data is a great option. Trig function, Zoom Trig is great. I mean, these are some presets, okay? What I did was I used Zoom Decimal, all right? And it just, helped me show that. I just wanted to demonstrate to you that there are indeed four different points where they intersect, okay? And to find those points of intersection, okay, I'm just keeping these other points away because, they are the coordinates of the maximum and minimum. I'll just hide them away. I don't want it to confuse. I don't want you guys getting confused that. So here we're looking for the 4 points of intersection. The way to do it is menu, analyze graph, and there is an intersection here, number 4. If you do this technique, you'll get 1 point of intersection at a time. All right? I prefer the other one. I mean, there's nothing. It's just a general preference. All right? So if you go on this analyze graph and intersection here, you will go through 1 point at a time, 1 point at a time, as opposed to if you were to go from menu, geometry, intersection points comes under points and lines. So I'll just back up again, all right? Menu, geometry, points and lines, and there's intersection point number 4. Can you see that? Now, why do I prefer this is because here, I just have to choose the 2 graphs. Look at that hint. It says, click on the first graph, then they're on the second graph. So the first graph, whichever one I call my first graph, okay? So blue graph is my first graph, red graph is my second. And look, I've just touched it. I've not even clicked it. I just touched it and all the 4 coordinates are there in one go. All right, I'll back up and show it to you again. This is from the geometry option. Okay, so menu, geometry, points and lines, and intersection points. If I just choose that, and this time I'll choose, red graph as the first one, and then click this one, and by the time I've clicked that, all the 4 points have appeared in one click, and that's why I prefer this one, all right? And the examination point of view, time is of essence, so the 4 values of x are negative 2.82, 0.364, 4.23, 5.76. Who's it? Somebody asked the question, what is Zoom Decimal? Sorry? Did someone say something?
About to, tell this question.
It's a preset. There are Zoom presets. Just like you have different. It's a different presets. So if I not on this, sorry, it's on the Zoom number 4. So if I go on Zoom standard, if you'll see it's like 10 by 10. I think Let me. Yeah, can you see that 10, 10, and then -6? Those are standard presets. Now the reason I chose Zoom decimal is because I think I've tried it once before. I don't exactly know what. Let's just look at the preset. I think it's wider than -10 to 10. So if I go on menu and I go on Windows Zoom and I go to let's try Zoom Fit. These are just presets, okay? So, that's -10 to 10, but then it's, can you see the Y values? That's just, they have, what I mean by preset is that the window settings, the X setting and the Y setting, when we go on menu and window and you have those window settings, there are some presets. And so Zoom Decimal is a certain kind of a preset. I would say just play around with your, can you see that? That's -32, 32. It's just one kind of a preset, and because I've used it so often, sometimes I know which one to go to, and it's for you to just explore your TI Inspire, just see, play around with it. Because yes, you can pinch the graph. You know what I mean by pinch the graph. You can drag this thing and look at the graph and zoom this way and that way. That's just toying with it, and I'm trying to say from that examination perspective, you just need in clicks. In one click, like you saw the points of intersection, or if you want to see, because the reason I even chose to show you that Zoom Decimal is because, the question says 4 values of X. And in the window settings that they've given, you couldn't see it actually. If you recall, you all remember that? When you could only see the 3. And, you shouldn't freak out during the time of the exam. Hey, there are only 3. Where's the 4th one? Or maybe you'd say there's no 4th one. But, to be sure of it, how do you check? How do you use the calculator even to check and say, yeah, there are 4 values? And, what's the best way to, try and identify what the 4th one is? That's why I showed you what that window, that Zoom Decimal was. Hope that answers your question, Hitesh. All right, cool. All right, cool. I'm just going to show you this question. All right, I'm not going to go through this question right now because it's another question on graph. But I want to show this because for me, honestly, I think this is the icing on the cake. This is where what do you call it? Exponential functions and logarithmic functions. I think this question is more on exponential rather than log. I think I had one more question open for you. Let me just check quickly. That was a modeling question on logs. One sec, let me see. No, not quite. But yeah, this is where I think it gets a lot more fun, where you have to come up with equations and models. So the first part might be very obvious. It says Rosie's grandmother gave her $10 on her first birthday. On each birthday after her grandmother gave her $5 more. Looks like a arithmetic progression. Anyone has done sequences and series? In fact, one of the first earlier sessions was on sequences and series, I believe. So in your school, if you've done sequence and series, it looks like that. It looks like an AP. The first term is 10, and on each birthday after, you get 10 more than she gave in the last birthday. How much did Rosie receive on her? Received from her grandmother on the 5th birthday, and you got to find out, 5th term, and then it says write a model, and then obviously you can write using your knowledge of arithmetic progressions. Use your model again. Use your model to calculate what happens. When did she get $105? It says on the 20th birthday, but you got to verify your model. Then there's a total, and then another model they've come up with. A model. All right. So there's another model here. Okay, I'm just showing you what kind of question to expect in paper 6. So part A was they've given you, or the first part of the question was they've given you a situation and you have to come up with a model which is simple. It looks very simple to you, right? Question number 2 is to verify that model that you had come up with. Question number 2, part B, they have given an alternative model, a secondary model. Number 3, another person, that was Rosie, this is Zahari. Zahari's grandfather gave him $10 on his first birthday. Same amount, right? Yeah, Rosie also got $10 on her first birthday. What happened after that to Zahari? Zahari, on each birthday after that, Zahari's grandfather gave him 10% more. Now that rings a bell. That looks like the compound interest question. And remember what I said at the start. Compound interest is a special case. It's just a special case of this exponential functions. how much did he receive on his 5th birthday? And students will guess that one also because it's compound interest. First one, what's that girl's name? Rosie's case was a simple interest question, and Zahari's question is more like a compound interest. That itself, you'll be able to do it. But number 4 is where they've given you the alternate model. All right? They've given you a model, and that looks like an exponential function. And actually, if you break it up, it is actually that compound interest is, can get, and you got to write down the explanation, all right? Number 5 is to graph that question, which you've seen, and then part of number 5 is to use the graph, okay? How to use the graph to answer the questions. We don't have time to do this thing, but definitely I can tell you that, maybe one of the next webinars, topics already planned out, but one day exclusively we should do something with paper 6. And at that time we can come back to this. But all I wanted to show with this question, my idea was not just to solve, because the time allotted in the exam to solve a complete question, because the 1 and 2 might seem very simple, but it gets tricky as you go to 5 and 6. That's where you got to where the calculator plays a bigger role. Okay, you got to write down. Look at that. It changed the model, and it says find the value, and so using the calculator keys, it'll come out much better here. My point was just to show you where is this and how this exponential function is going to play out in your IGCSE exams. I just thought maybe it will be a good idea to give you an overview, and maybe tell you that maybe some of the one of the other days we will talk about paper 6 in particular. And paper 6 is not just exponential and logarithmic functions, don't get me wrong, but that's where you will see a lot more of the application of the logarithmic and exponential function as far as the IGCSE is concerned. I'm going to stop here because I'm going to just take some questions now. All right, I've spoken enough, and from anything that we've spoken or anything regarding the IGCSE exams and exponential functions that we've discussed, if anyone has any questions, I'm happy to take your questions right now. Or about the calculator, main thing is about the calculator, right? How are we using this calculator, the keys that I showed you? No questions. Let me ask you a question. Are you sure nobody has a question? No one has a question? I'm going to ask a question if you don't have a question. Ready? Okay, I'm going to throw a question, and maybe it is something that, let me just hear you guys say. Now, in my agenda, I had written a word which I thought I should say, because this and I did not say, because normally in my class whenever I teach, I spend one complete day just talking about that, so it's one entire topic for me, but if you can see this word and tell me what that means. What is that word? Asymptote. What is an asymptote? We spoke about everything else. In the background, I gave a nice history, showed you video, a nice story. You must have heard it before. We spoke about the graphs and all. We did some problems, and I exposed you to, the paper 6 kind of a question. Well, what's an asymptote? Anybody in this group? A graph that bends towards 0. A graph that bends towards 0. Okay. Anyone else? Anyone else? Don't feel shy. Just type it down, but doesn't touch 0. Okay, graph that bends towards 0 doesn't touch 0. Okay, anyone else? Okay, Swati, if you can make a note of it, one day we should include this. This is something important, okay, to talk about asymptotes for IGCSE. One complete day we can talk about asymptotes actually. But because I brought it up, I stirred the hornet's nest, I'm just going to say that very quickly. And why did I include it in this topic? An asymptote is actually an imaginary line. Okay, that's just a start. And the reason I'm using the word imaginary line Sir, we will have a question. Okay, sure. The reason I'm using the word imaginary line is because even your calculator will not show you when you graph it. Okay, because sometimes when the question says, let's say if the question was, I'm just making a very simple thing. Okay, let's say the question was graph f of x is equal to 2 to the power of x. Just a very simple graph. Okay, and you'll say, all right, calculator is allowed. Let's use the calculator. So you jump to your calculator and you say, okay, I want to draw the graph of 2 to the x. I think I've put some graph paper here. Here maybe. Okay, here you go. Let's just type in 2 to the power of x. 2 to the power of x. 2 to the power of x, and there you go. I graph, and you copy down the graph as it is. If the question was out of 3 points, if this question was out of 3 points and you just graphed it just like this as you see on the graphing calculator, let's just make it a little interesting, okay? Let's say it was 2 to the x plus 1, okay? There you go. And let's say you sketch the graph as it is, and the question was out of 3 points. You know how many you'll get? You'll get 2 points. Okay, if you sketched as it is, because like I said, it's an imaginary line. Even your calculator will not show you the asymptote. So I showed you this graph on the calculator, and it was something like this. Let's just draw that. Okay, it was something like that. Now, what was missing? If you just copy that graph just like that, what was missing was you should show a dotted line. You should show a dotted line, and that's y is equal to 1. Okay, that line, that imaginary line, is an asymptote. In this case, in an exponential function, you have a horizontal asymptote. Exponential functions will only have horizontal asymptotes. Logarithmic functions will only have vertical asymptotes. And the topic of asymptotes is not just for exponential and logarithmic functions. Even if you have a function, actually, when you have a function which is a rational function, okay, so you have something on the numerator and something on the denominator, okay, so x squared, blah, 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 and then you have x minus some a, x minus some b, something like that. Here also you have asymptotes. So all I'm trying to say is that asymptotes is not just a theory that's restricted to exponential and logarithmic functions. It even comes in rational functions. So I think on some other day we should touch this because you have questions. Even in your IGCSE question paper, it says write down the equation of the asymptote. And because the calculator doesn't show it clearly, it's an imaginary line. And who said that? I think Adit said that. Yeah, it's an imaginary line. Let me at least complete that definition for you. It's an imaginary line that is not a part of the graph. I think you need to understand that it's not part of the graph. Okay? Because a graph is a set of all the y values. The graph is a set of all the y values. The imaginary line that is not part of the graph, and the graph either moves away or move towards it. Okay, and I won't give away more because we can discuss that later. Horizontal asymptotes a graph can cross, vertical asymptotes a graph will never cross. So some other day we can discuss asymptotes in greater detail. But as far as your IGCSE syllabus is concerned, I think you should be able to you would need to know about asymptotes also. And like I said, not just in the context of exponential and logarithmic functions. There are questions that come in the IGCSE paper where you ask to find the equation of an asymptote, and because it's an imaginary line, it will not get graphed. And you got to be able to find out the equation, So some other day we will talk about asymptotes in greater detail, in much deeper detail. Okay, I think I'm going to stop there and maybe just give them a couple of minutes, and we will then we can move on to any questions anyone wants to ask before I hand it over. Any questions, boys and girls? No. All right, cool. Swati?
Oh, yes, sir. Thank you so
Yeah.
much for the session.
Sure.
So I guess there are no doubts, so we can have a quiz.
No doubts means either they did not understand anything or
Yeah.
that's this case.
No, it was good. Yeah, I guess everyone have understood. So now students will conduct a quiz on what we have learned today. So I request all of you to go on your Google, open your browser and enter joinmyquiz.com. Enter joinmyquiz.com. I'll just share the code with you all once you're on the page. Please enter joinmyquiz.com and the code is 015918. 015918. Okay, I'll wait 2 more minutes and then we can start with the quiz. The code is 015918. Is anyone facing any difficulty in joining the quiz? All right, so I think we can start with the quiz. Let me just start the quiz. So keep your calculators in your hand. All right, here's your first question. Solve for x. An equation is given, you need to find the value for x. You can use the n solve feature. Seconds. All right, the correct answer is 9. Next question. You are given an image. You need to find the value of r. value of r. It's the same method. Alright, the correct option is D. So which is 10. Next question. Solve for x. Again the same procedure. Use n solve on your calculator screen. Alright, on top we have Vishuddh. And on second we have Vishuddha. And the correct answer is no solution. So the calculator will show you no solution on the screen. What's the corresponding graph of? Function is given the corresponding graph. Graph your functions on the graph page. Time up. So the correct answer is option 4. Next up we have what is the equation of the asymptote? So if you are aware of what an asymptote is, please answer. Seconds left. we still have Vishud on top. The correct answer is option 1, x equals -3. Next question. Very easy question. Logarithmic functions are the inverse of. I'm sure everyone is going to answer it correctly. Okay, so logarithmic functions are the inverse of exponential. Exponential functions. Find corresponding graph of input the expression in graph A. Seconds left. All right, the correct answer to this question is option A. Next question. Solve for x. So here I have given 2 minutes. So once you get the value of x, you will not get the value of x in terms of log. Find out the numerical value for each options and find out your answer. Seconds left. Correct answer is option B. Next question. So this can be done on the calculator page or on the graph page as well. So draw the graph of each and find the intersecting point. Seconds left. All right, all done. So Vishud is on top and Ishita is on number 2, and the correct answer is option C, 2. Solve using a graphing utility. So graph both the expressions and find the intersection point. You have enough time for this. Okay, that was so quick. So the correct answer is 0.273. First option. The correct answer is 7. Vishud is on the top still. Option 4. Daniel's print shop purchased a new printer for 25,000. Each year it depreciates at the rate of 5%. How much will the printer be worth in 8 years? So as Mr. John Paul had mentioned that you also have compound interest. So this is a question from compound interest. Make sure you read this depreciates word. Rate percentage is negative. So the correct answer for that question is option 1. Is the pictured graph growth, decay, or linear or none? Very easy question. So yes, it is exponentially growing. Exponential growth. So 6 of us have answered correctly. What type of function is this? Is it growth, decay, or linear? Plot it and check it. So it is again the exponential growth. Sketch the graph of this function x square by 2 bar x from 0 to 8. Also find the value of x for this equation. Basically, you need to draw two graphs, one for the LHS, one for the RHS, and then find the intersection point. can I have more than one answer? 5 seconds. So since we see it is x square, you'll have two answers, two values of x. So the option 1 and option 3 are the right answers. Alright, sketch the graph of this equation and find the value of x. So on top we have Vishud. The correct answer is option 2. Solve for x. Seconds. We just have 2 more questions after this. So the correct answer is +9. Okay, let us quickly complete. Rewrite. So it's given in the logarithmic form, convert it into the exponential form. 10 seconds. Right, time's up. It is option 4. And the last question for today. Use multiple log property to write as a sum or difference of these two logs. Five seconds. Yes, time's up. So let's see the board. On top we have Vishut Shah, congratulations, and on number 2 we have Adit. Alright, so I hope you all have enjoyed the quiz, and may I know, is there any doubt from the quiz session? Or maybe I could just show you one of the question, like the equation given and how do we calculate the value of x. Let me just share my screen. Adit, any doubts? Okay, so here you can see the screen of the calculator. So generally when we have, just a minute. Alright, generally we have to find the value of x. So what I was talking about was just go to menu, number 3 algebra, and number 1 numerical solve. So when I go on this numerical solve, this is the syntax. So in between the brackets we can input our equation. So let me take an example. Log. So here you can see log is about 10 power x. So all the blue letters, control plus 10 power x. So let's say log x to the base 3 equals -6. So we also need to inform the calculator that we are supposed to find the value of x. So you need to tell comma x. So once you have inputted the equation, just hit enter. So this is one way of finding the value of x. The other way is, let me create a graph page using control plus doc, and here it is a graph page. The same equation can also be done on the graph page. So we have two expressions given. Log x to the base 3 is the first one. So I'll just input the expression here Again control 10 power x log x to the base 3. Hit enter. Hit tab to again get the entry field. And what is the RHS part? -6. So just input -6. So these are the two graphs. We can just move the window according to our convenience. All right. So now we need to find the intersection point between the two graphs. And we see there's this intersecting point. So how do we go ahead and find the intersecting point? So everything you find is in under menu. Go to menu, number 6, analyze, and here you have intersection point. So as Mr. John Paul had mentioned that when you have more than one intersecting points, it is always advisable to go under the geometry section, points and lines, and here you see intersection points plural form. See, which means if you have more than one intersecting points, all the intersecting points can be calculated at one go. So either way, even if I use this now, it will automatically get me the solution. Click both the graphs. Yes, and here I have the solution. Okay, so this is, I need to just change. It was -6. Yes. So this is how we calculate. So either way you can find it on the calculator page and on the graph page. So I suppose no more doubts. So the next session will be again on the next Saturday, that is 28th of November. So that will be again based on the functions, on the application of functions. So yeah, we will send you the templates, and the Zoom link are the same for all the webinars. So use the same Zoom link to join in for the next webinar as well. Thank you. Have a nice day.